structures. Before it starts, let me remind you that today, after the third talk, after the talk of Christophe Copper, around 5:15, there will be an informal discussion with Antti Kupiainen, who will give a sort of extra informal lecture on the connection between Wilsonian renormalization group and SPEs. So, please.
Thank you. So, let me first start with the slides to recall where we are. So, today, essentially, I would like to go back to the pointer doesn't seem to be very strong. So I would like to go back to the reconstruction result and give you a proof of it, and then also kind of repeat, go over the integration statement again, and also sketch a proof of that one, to show you a little bit what's involved in on the more technical side. So this doesn't seem to work. That perhaps I don't necessarily need it, but so. Here is the reconstruction statement. So so the purpose, in a certain sense, of introducing model distributions was the following: if the order of the model distribution is positive, then it uniquely defines a real distribution, given the model, of course. So so behind every model distribution of positive order hides a real distribution. So that statement makes the connection between this scaffolding for a real object and a real object, and the connection is as you would expect. Model distribution given a base point locally describes a distribution. So, so model distribution describes a one-parameter, a family of distributions which are parameterized by the base point. And now you're saying that the output is close wherever you are in space. It's close to the corresponding element of your family. So that's what this is. That's what this is really stating, and it's expressing. Closeness in a weak sense by looking at this family of averaging functions. And as I already mentioned on the blackboard last time, or even the time before, that there is kind of you can forget about the algebraic structure of the model and a model distribution. How you should really see this as an analytical statement is that you have such a family of distributions which are indexed by the base point in space, which satisfies a graded continuity condition in this. Thank you. Which satisfies a graded continuity condition in the base point, in the sense that if you look at the difference of this the difference between of this field of distributions for two different base points, and you look at kind of a weak distance between these two distributions, then this is estimated in the following way. So parts of this difference is estimated in a very weak norm with a good Hölder exponent, and other parts are estimated in a somewhat less weaker norm with a somewhat worse Hölder exponent. But the important thing is that these two exponents always sum up to 1. So that's the thank you. That's the condition, and here I restated the theorem on the level of this on the level of what I just said. So the input is a family of distributions, and the output is a single distribution. And now I want to here it's on 2 pages. I want to give you the proof of this on the blackboard because it can really be done quite efficiently. So perhaps if you could move on up the screen, the person behind. Okay. So let's let me state the reconstruction theorem. In this fashion. So we're given a family of distributions which indexed by base points x, which satisfies this continuity property. So if we average it on scale lambda around to one of the two space points by looking at this application or integral, then this here is estimated, I can set the constant without loss of generality equal to 1 by a finite sum over exponents alpha, which of course are in our homogeneity space, lambda to the power alpha, x minus y to the power gamma minus alpha. So both this exponent is always positive, this exponent is typically negative. And so that's the condition together with lambda is positive. And the statement is that there exists a uniqueness was clear, so let's talk about existence. There exists a a distribution, a single distribution, which is close to this family in this sense that if you look at this difference in the neighborhood of a point x, and you look at this average, then you want this to be less than lambda to the power gamma, which is positive. So that's what we have to prove, and so a simplification comes about when you restrict yourself to averaging functions which are Gaussians. That because the involved distributions are of finite order, you can always kind of realize that by an approximation arguments of a general Schwarz function by kind of a convex combination of Gaussians, you can restrict yourself to this case. So restrict to case of phi being Gaussian convolution. And what's the advantage? The advantage is that you have what one calls the semi-group property for these convolutions. So if I look at the Gaussian in kind of base point x, and now I'm thinking of it as being the heat kernel. So at time t, which means length scale squared of t, or let me rather take capital T minus little t, because I need two time scales here, y, and then I convolve it with the Gaussian at time t by performing this integral. I get the Gaussian at time capital of t in x at z. That's the usual semi-group property. So so this suggests to look the following integral, to consider the following integral. So let me call it I little t x capital T, which is a little bit modeled after the semi-group property, t minus little t y integral phi y little t z f of y dz dy. So I'm integrating in z and in y. So now, why is that a good integral? Because on the one hand, if we let t go to 0, we want this limit to exist. So this is something we need to show. And if it exists, it should morally correspond to phi x square root of t, y the reconstruction f averaged over the length scale over with the time scale t. And on the other hand, if we look at it at little time equal to capital T, then we recover the other term here. X square root of t z fx dz. So what we need to show, the task we need to show is that this limit exists. So let me just express this by writing it down. And we need to compare its distance to the other integral. And we want to show that this is less than square root of t, which is the length scale to the power gamma. So that's really the statement of the theorem translated with help of this integral I. And now comes something which is inherent in all proofs, a dyadic decomposition. So because the exponent is positive, it's enough to show that it's enough to show that for fixed x and capital T, if you compare to dyadically separated little t's, that this is estimated by this little t to the power gamma. So if we have this, then by the triangle inequality and convergence of this geometric series based on gamma as positive, we get that this limit exists, I mean Cauchy sequence criterion, and we get this inequality. So that's all we have to show. And now that's quite easy to show. So let's write this down. I xt t over 2 minus I x tt. So those are two, let me just copy the definition, two convolution integrals t over 2 y phi y square root of t over 2 z fy dz. And let me write the other one with a different variable, t minus t square root y prime. So here I should write dy, and here I should write dy prime, phi y prime, t over 2 z fy prime dz dy prime. Now you want to bring them kind of onto the same level, and the only difference is that you've kind of partitioned your time axis in two different ways. From 0 to t, you've been at little t and at little t over 2, and for this integral, you went from here to here, and then from there to there, and here this is t. You did it with this point. And now, of course, it's clear what to do. You split it into these three parts. And so you get, this allows you to get a single integral, y phi y square root of t z. And I have to be careful. And better would have looked it up. This is an integral. This is phi y prime square root of t, and then I get f of y minus f of y prime dz dy dy prime. And here I should take, this should be y prime and this should be z. So that's just using the semi-group property, which I stated down here. So now I've split this interval into these three pieces, so therefore I get kind of 3 times the convolution. And now I'm done because by the continuity property, I know that this inner integral, that's exactly of this form, with y playing the role of x, and y prime playing the role of y. So I know that this inner integral, after I put absolute value bars around it, is less than this sum square root of 2 to the power alpha y minus y prime to the power gamma minus alpha. So here I've just used the assumption. Okay, now what am I left in? Now let's look at the next integral. So the integral over y prime. So now I'm integrating this moment. So the difference between y and y prime over a Gaussian that's centered at y in y prime. Right? And therefore, up to some constant, this will be less than alpha less than gamma, square root of t over 2 to the power alpha. Then this length scale, square root of t to the power gamma minus alpha, which of course is comparable to square root of t to the power gamma. And the outer integral, nothing is happening here because I have already estimated everything by this constant. So I get that this entire integral is less than square root of t to the power gamma. That's the proof. So reconstruction with the semi-group approach, reconstruction gets that easy. I mean, there's nothing that I didn't hide anything under the carpet. Yeah?
So here you showed that reconstructed the distribution against these averaging functions.
Yeah.
And then how do you show that it all comes from a bona fide distribution?
Okay, so that's a compactness statement from this characterization. So this is kind of then soft analysis. This is no longer about estimates. From this inequality, you know that the order of this distribution couldn't be worse than the worst order of these distributions. So you learn from this that that formally kind of the object which you constructed behaves like a distribution of a finite order, and therefore you have a compactness statement, and that allows you to go to the limit in this parameter little t. So that's a soft compactness statement on distributions, which are of finite order and are controlled. Okay. But the estimate in the end, in this business, one cares about estimates. The estimate really is there. Okay, so now I would like to go back to the slides and return to integration. So if you didn't have the time now to copy, exactly the same lines are on the slides. So here again is this proof, which is from a work of Hendrik Weber and myself, when did we do it? 2016, must be. So about quasi-linear equations. It triggered a paper by Gubinelli and co-workers, by Martina Hofmanova and co-workers, by Martin Heyer and co-workers. It was rejected once. It's still not completely, we don't know the fate of it. But I think it contains a couple of interesting ideas And there's also kind of more general work with Scott Smith, who's here, and Jonas Sauer. Okay, so back to integration. So let me briefly remind you of the abstract setting of Martin Heyer, and then let me explain again the integration theorem, and let me show the proof. So remember that regularity structures, in a certain sense, live on these three levels. There is kind of the completely abstract level of a set of homogeneities of an abstract vector space and the structure group. Then there is the level of the model. So this map P, which kind of takes an abstract placeholder and transforms it into a base point and transforms it into a living distribution, which vanishes to the right order at the base point, and the change of variable object gamma, which has values in this group, and then the space in which one finds the solution, in which one defines the fixed point argument, which Lorenzo was mentioning in his talk, which is the space of model distribution. So those are the three layers, and now an integration structure means first to have something on this very abstract layer. So just a linear map on these abstract vector spaces, which kind of shifts the homogeneities in the right way, which vanishes on polynomials, and which almost commutes with a structure group, in the sense that the commutator kind of just maps into polynomials. So those were kind of the three conditions, and I gave you what it. I didn't. Where's the slide? Okay. So we checked this in case of our toy example, that indeed one has this commutation relationship, and then there is kind of on the second level, when it's about the model itself, there is this object J, which now takes a base point x and spits out a polynomial up to a certain degree, which depends on the homogeneity of the placeholder it takes in. And it's made such that on the abstract level, if you add to the abstract integration map this J of x, you get an object which, when you transform it into real life, solves your partial differential equation with the corresponding right-hand side. And we've seen in our we've computed it in our toy example what the J of x is. So that was the second level. That was the dealing with the toy example. Then there is, and I will get back to this. There is one important relationship between more or less on the algebraic level, some intertwining property, which shows you that kind of the natural object is really the I plus J of x, because it has the right behavior under coordinate transformation, and the argument for this, let's do that together. The argument for this goes as follows. So we know that if we look at the difference of these two expressions, that it must be in the abstract polynomial space. Why is that the case? Well, by the postulate on I, we know that the commutator of I and an element of the structure group maps into polynomials. First thing, we know that J maps into polynomials. Second thing, and we know that gamma maps polynomials or abstract polynomials into polynomials. So this, whatever this difference is, if it's not zero, we know by all the assumptions we have that it must be a polynomial. So in order to show that it's zero, it's enough to it's enough to evaluate this abstract polynomial at a given base point, let's say x, that's convenient and show that the resulting actual real polynomial vanishes. So it's enough to show this. So we apply our model pi of x to this object here and want to show that this is equal to 0. We use the change of variables formula for the model, and we see that here's a bracket missing, that we get this expression. Now this is a real object. So this is for fixed x and y. This is a polynomial, and in order to show that it vanishes, it's enough to show that our massive operator applied to it vanishes, and that just follows from the definition of J that this is exactly the correction which gives us a solution to the PDE. So if we apply the partial differential operator to it and use again this property here, we see that it vanishes. So so that's part of the definition, and that's a good exercise using kind of the little things in the definition to show that one has this this intertwining property. So here is kind of the slide on the integration. That's essentially what I said before. So so now what's really the goal? So we're given a model distribution of, let's say, some positive order. We know that behind of it hides a real distribution, the reconstructed distribution, RF. And so that means we can solve the equation with this right-hand side. And now the goal is to get a good understanding of the solution, to write the solution as the reconstruction of the model distribution, which is in the space with two gains of regularity. That was kind of the type of basic reasoning Lorenzo was using when setting up this fixed point argument. Just in his case, this was not the elliptic operator, but it was the parabolic operator. But things don't change much. So so we want to understand this object phi. So something we know is that by definition again of I and pi, of I and j, we know that if we subtract from it this object here, then we make the right-hand side very small, close to the base point. So we know that if from phi we subtract this correction, we get the modeled distribution minus its correction, and that by reconstruction is very small. It's weakly small to the order gamma in the distance to the base point. That's what we just proved. And now there is a simple PDE argument, which you also can do with using kernels, is that there exists a polynomial of degree strictly less than gamma plus 2, that this object corrected by the polynomial vanishes to order gamma plus 2. So that's an outcome of a simple analysis argument. And now it's clear what you want to do. That's how you want to think about your reconstruction of the solution. So you define calligraphic K of f as the sum of these three terms. The first term being completely algebraic, just the abstract integration operator. The second term taking care of the model, so that the model satisfies the PDE. And the third term being kind of a correction term coming from your model distribution, so that the model distribution kind of does the right thing. And integration states that this object, which you wrote down here, indeed defines a model distribution of the right order. So, so the last thing which I want to convince you of, that this formula here defines. Perhaps I write it on the blackboard. Defines a model distribution, which means we have to check the continuity condition. Because in the end, everything has to be quantitative, because you want to set up a fixed point argument. So you want to write down norms. And of course, as Lorenzo said, sometimes you may forget about plus 2 and just think about plus 1. But nevertheless, you want to control the appropriate norm of these objects. So let me recall the let me put this on the blackboard. So script k of f is defined in the following way. You look at I, the abstract integration operator, corrected by j of x. You apply it to f of x, and you add this non-local correction. This is how it's defined. Thank you. And the theorem 2, the integration theorem, states that if f is in d gamma, you want script kappa f to be in d gamma plus 2. And perhaps I also write down the definition of NF. So the characterization of NF. So NF is something which is in the abstract polynomials up to order gamma plus 2. And it is done so that it gives you a good approximation of your solution phi, in the sense that this entire thing, if I apply the model to it, that this here is small of order gamma plus 2. So those are the two important properties of n of f, the defining properties of n of f, which is sitting in the definition of k of f. Okay. Is there a question? Okay, so here comes the argument on no, that was something which I already perhaps mentioned last time. In case of our toy example, we can compute exactly what this correction term is, or in fact it's more natural to put both polynomial terms together, and they were given by these expressions we looked at already last time, and we showed by hand that together with the non-polynomial part, this was indeed defining a model distribution of the right order. So in case of our toy model, we did the calculation. We kind of have, in case of the toy model, we have an independent we independently check the outcome of the theorem. But now this is kind of 2 slides on the proof of the theorem. So here again is also what I wrote on the blackboard. The definition of this reconstruction operator on the level of model distributions. And now we have to check the continuity condition. So remember that what we need to do is we need to, if we want to show that k of f is a model distribution of the right class of continuity, what we want to show is we want to compare kf at x to kf at y, and as we keep stressing, you shouldn't compare them directly, but you should compare them after transformation, and then you should expect a type of graded continuity condition, where that if you look at the coefficient in front of the homogeneity alpha term, this should be estimated. This should be of the order of x minus y to the power, the order of the distribution, which here is gamma plus 2. That's what we want, minus alpha. So that's the condition. That's the condition we have to check by definition of what it means to be a model distribution by the continuity condition. And now, so that's the expression we need to control. That's the definition. So there is this non-polynomial part, and there are 2 polynomial parts, and there was the interesting intertwining relationship, which allows us to rewrite this difference as the abstract integration map applied to this expression, which is nice because that just refers to the continuity property of the input distribution f plus a polynomial term. So going from here to here just uses the definition and crucially this intertwining property. So, so that means the expression we want to estimate comes in form of this term, which is non-polynomial, and in form of this term, which is polynomial. The non-polynomial part is okay, because that's almost tautological. I mean, there is nothing, I mean, that's not a deep insight. I mean, things are set up like this. So if we look at the homogeneity alpha plus 2, since I maps, since the crucial property of I, the first crucial property of I was to map T alpha into T alpha plus 2, and since these spaces are finite dimensional, and therefore any linear map is continuous, so let's say modulus 1, we know that the alpha plus 2 component of I times something is estimated by the norm of the alpha component of the something. So that's just tautological. And then we again plug in the definition of what it means for f to be continuous. And that's sitting here. So, so that means on this part, we have exactly what we want. We have this gain, so if we write this exponent as gamma plus 2 minus alpha plus 2, we get exactly what we want. So in this part, we're fine just by algebra. And so again, all the interesting stuff happens, all the analysis, all the work lies in the polynomial part. So we want to show that the polynomial part is also continuous. So we want to show that if we take this object and we look at its kth coefficient, so in front of the abstract monomials of order k, we want to have this, this estimate for all k's up to the maximal order. But since this is a polynomial, such a strong estimate is equivalent to a weak estimate. On polynomials, that's the same. We don't lose information. So it's enough to use it in this weak form. But since we're using it in this weak form, we can kind of plug this back in, because this part here, by the continuity properties of the model, has already the right estimate. So since this part is okay, we can smuggle in the remaining, this part which we threw out in the first algebraic step, we can smuggle it in into this final analytic step. So in the end, we just have to show this weak continuity property. So we passed from kind of a strong, the wish to prove a strong continuity property, to this averaged or weak continuity property. And here, right. And in doing so, it's convenient, and I may reduce to myself where this averaging parameter has exactly, is exactly of the size of the distance of the 2 points I'm being given. So that's what we want to get at, from strong to weak. And now that's again, that's easy. So here is again the definition of what this n of f was achieving, or the k of f was achieving. The k of f was achieving exactly this property. It should be a good approximation to the solution phi. Perhaps I should also write down what phi is. So phi is like in phi. I'm using the letter phi as in the toy example. So phi just solves this PDE. So that's the how it's defined. It's defined to give you a good local approximation to your solution in the weak sense. And that's what we. So that's good, because we want to get a weak. We just need to get this weak information, this weak continuity, and we're given this weak input. And now it's just a matter of telescoping property. So we want to estimate this blue expression in a weak norm. So we write this blue expression using again our transformation of model. We write we pull the pi on the first term, and we pull the pi on the second term. There it becomes pi y. So we get this term and this term. But then we smuggle in the solution. We can, right? It drops out. So so therefore, if the green terms are small, the blue term is small too. Now there's the little twist. The first green term is exactly as we wanted, because we want to look at averaging functions which are centered at x, and here we have the base point x. The second green expression doesn't look right, because we have the base point y, and but we're averaging at x. But now we should remind ourselves that the averaging scale was just the distance between x and y, and therefore an averaging function centered around x can be considered as an averaging function centered around y, with essentially the same scale. So, so for the same reason, both of these terms are small, and therefore the blue term is small, and therefore the continuity is proven. So that's the proof of the integration lemma. And again, it follows essentially a little bit the ideas from the papers with Hendrik and Scott in Martin's paper. It's done differently by using the kernels and kind of using kind of near field and far field decomposition, which is just a different way of doing it. I personally find this here a bit more transparent, but that's of course a matter of taste. Okay, so that's probably earlier than what I wanted to do. I could have done that on the blackboard. Okay, so that's essentially, unless Lorenzo wants me to explain something, because I'm done with my program.
You can give me back the 5 minutes you took, yes?
Yeah, right. I'm happy to do that. Sorry?
With interest.
With interest, yes. With non-Draghi interests. And very good. So yeah. So I stop here, and perhaps there are questions.
Questions, comments? Yes?
Did we solve the initial equation?
What do you mean by the initial equation?
I'm not sure. I mean,
so now that's a question to in a certain sense, both of us, right? I mean, if you mean by the initial equation the 5-4-3 model.
No, I meant the toy model.
Yes, but the toy model, I mean, in terms of solution, that was never an issue, right? I mean, since it's a linear equation. On the level of the toy model, and that we did on the first 3 slides, the issue was really understanding how the solution looks like, and in a certain sense expanding it. I mean, I can go back to the first slides. So on the level of the toy model, the issue was really, I mean, that the solution, I mean, there's nothing to show in terms of existence and uniqueness, but everything about understanding how the solution looks like. And the strategy of regularity structures, no matter whether it's in this toy problem or whether it's a kind of the ambitious nonlinear problems, you want to use a certain finite number of building blocks to describe your solution, and so the building blocks were in a certain sense suggested to us by Leibniz rule, by kind of canceling a little bit like, you know, I mean, da Prato de Buch. Canceling this bad term, and the outcome was that indeed we could understand the solution, which we knew ahead of time it existed. We could understand the solution as in parts completely local. So that's the first part, and in a part non-local. In a non-local part, right? And this understanding, this writing the solution into local and non-local, we later then kind of had a second pass at this, where after introducing the regularity structures, that's example 3, with 1 term less, we now, the same understanding we had before, we now expressed in terms of regularity structures. So, so there was the first part, which in a certain sense was completely algebraic, where we just applied the symbol I to the previous symbols. And there was a second part, which was analytic, and which spits out the polynomial part. And then we gave the argument that indeed this model distribution satisfies the continuity condition which you need, which you want for model distributions. And in the end, that was relying on our very first insight that after subtracting these functions, we get something much smoother. So that was a long answer, and I don't even know whether I answered about the question.
Yeah, but what I meant is even if we knew from the beginning that there was a solution and that we, maybe with all that we've done, we can find this again. So we got enough of a Taylor expansion of this solution and we apply this reconstruction theorem and here it is.
Sure. So one little detail we could have now, one little improvement about this very initial treatment would be that initially we thought, okay, EDA is C infinity compactly supported. I mean, this much more kind of precise treatment we did here would tell us that EDA has to be a little bit better than C2 to run this program, and we would get the right mapping property, kind of the C2 plus epsilon norm of EDA, then into the D5, the D4 plus epsilon norm of this model distribution if there were this third term. So there would be a bit of an improvement over what we did initially. But again, I mean, this toy problem was just there to make it easier to understand these objects and to stress what I think is, from PDE point of view, an interesting aspect of regularity structures, that you're using that kind of the singularity shines through. Kind of, which is exactly, I like very much this formula here with kind of one algebraic and one analytic part.
To verify if my understanding is correct. So you said that in the original proof of hierarchy, the integration theorem, they just do it in a different way, and it's just a matter of taste. But the way I understood your argument is that you do not have to decompose the kernel into K plus R. What Lorenzo mentioned, you can get by without doing that. Is that correct?
Here in this, in kind of this, I mean, the part which I kind of oversee, that's not necessary. You don't have to. You don't have to do this.
Okay. And do you know if in the rest of the theory, do you at any point make, well, except at this point that where you get rid of it, do you make reference to this kind of decomposition? Or
I don't. Perhaps Lorenzo can address this later. I don't know the rest of the theory that well. I mean, my knowledge about all of this is kind of related to quasi-linear equations, which is kind of a very specific situation which doesn't fit into the usual framework, and there we never. I mean, we work. So so the lesson we learned from that work is don't try. I mean, our take on it is don't try to work with integral operators, but take the PDE. I mean, also as a PDE person, of course, I like this. So I think sometimes there are advantages to I mean, using the fact that you're actually dealing with a PDE.
But then it would not just be a question of taste, but then you could really get rid of decomposing the kernel, right? So you spare yourself substantial.
Yeah, okay, but I don't want to. I mean, so I don't want to make that.
Okay, but at this stage you don't.
I mean, it might be interesting to check.
The first example, the structure group was a billion. The second was non a billion. Does this matter at any point, or?
No. So I mean the difference was just that in the second. I mean, the second example we went one step further, and so second derivatives started playing a role, and then it became non-abelian. But I don't think that this makes. I mean, it certainly doesn't make a difference for all the things which I presented, whether it's abelian or non-abelian.
So really, you don't really need to know what the structure group looks like, right?
Not for I think it's important to know this when you're actually trying to build the model. I mean, here, I mean, in a certain sense, all I'm presented here was in a certain sense, let's say, a more or less easy part, because I mean, besides the toy model where we could do everything by hand, I just postulated what the model should satisfy without never checking it, right? And then when you want to build it, then at least that's what we find in kind of the application I know. Then it's important to have a good understanding of this algebraic part.
More questions?
So renormalization didn't play much of a role here because, as you pointed out, the problem itself was not problematic at all.
The toy model, yes.
But once you've set up all these structures, of course, you can still play around with renormalization groups. Renormalization corresponds to tweaking the higher levels that you have identified them. So in principle, you could go ahead and relate this to this talk of Lorenzo by studying, identifying the corresponding renormalization groups here.
So you mean for this toy example?
Yeah.
That might be an interesting exercise. I haven't done it, but yes. And I think you will now talk a little bit about the renormalization group itself on the level of the 543 model. No, so I haven't done this. I haven't done this for this toy model. I don't know whether that's an interesting exercise.
More questions or comments?
In this case, you can compute explicitly the coefficients in front of the polynomial placeholders. In general, you cannot have such nice expressions, can you? For more complicated equations.
I wouldn't expect this to. So the fact that you can, the fact that in the end also for the remainder terms you're solving a PDE and you can express it. That you get up to such an object. That's I think that's generic, but the fact that you can then very explicitly understand the x dependence of that object, I think that's due to this simple example, and I wouldn't expect that to be true in general or for interesting examples.
Okay, I guess let's thank Felix again.